Okay, so we are we are continuing with interval estimation. I put all of the tables, the T and the Z table that we're going to need for this topic directly in here, but they're also posted on the Lima for you guys. The T table is what I'm starting off going through, explaining what information does it contain. According to the picture, it tells you the T distribution is bell-shaped, just like the normal distribution. You have a T label on your x-axis. And the shaded region, or the area or probability, is to the right. And you'll notice that the label, the first label that you see that I highlighted, is upper tail probabilities. So it tells you these are probabilities to the right of your T value. Remember that with the Z table, the standard normal table, these were probabilities to the left of your value that you were looking at. And so the two tables, the pictures look similar, but one table gives you left-tailed or less than probabilities. The T table gives you right-tailed or upper greater than probabilities. Some other details, you'll notice that the column label for the first column is DF. You've seen that before with the chi-square distribution. Anyone remember what DF means?
Degrees of freedom.
Perfect, that's your degrees of freedom. The degrees of freedom for the T table are simply n minus 1. So it's 1 less than the amount of data that you have. So simple to get, you just have to remember to subtract 1. So your degrees of freedom, according to this table, are 1, 2, 3, 4, up through 1,000. I mean, there's some gaps. Notice that it jumps from 30 to 40 to 50, 60, 80, 100, and then 1,000. And so it's not perfect, but it's got a lot of relatively small sample sizes, or at least degrees of freedom with respect to sample sizes. The other thing is that your first row are your probabilities. These are the upper tail probabilities. So what is the main body of this table then? Anyone have an idea? And the reason I ask is because the Z table, the main body, were your probabilities. And your Z scores were the first column and first row. So we know where the probabilities are. We know where the degrees of freedom are. What's the main body?
The critical values.
Yeah, these are your critical values, or T scores. You could call them either or. And so it's important to know where things are in the tables that you're going to be using. A lot of students do tend to use this bottom row, which are confidence levels. I'm going to teach pretending that that row doesn't exist. Students tend to find it anyway and use it as a crutch. It's not a recommendation, at least if you plan on taking another stat course after this, because it'll hurt you in the long run. So if you do know that you've got another statistics course coming after this one, try to learn how to do what we're about to do without using that bottom highlighted row. It'll make things easier for you in the long run. All right, so last class, I did kind of go through this table, and I said, either you're doing a confidence interval for mean or a confidence interval for proportion. If it's for proportion, there's only one choice, so it's very easy. But if it's for mean, there's two choices, and you need to decide which one to use. And the fundamental way of deciding is if you have the population standard deviation sigma, use the top one. If you don't have it, you must be able to get the sample standard deviation S, which is an estimate of sigma. Remember, S is a point estimate of sigma. And you would use the second one there. So we had gone through this first problem, and we solved that one. We realized that sigma was given. It was nice enough to even label it for you guys. Usually I won't give a label there. Jump to problem 3. Problem 3 is going to be very similar to number 1 that we did last class. Read through and tell me what's different. All right, so you guys had time to look at this, think about it, compare it to the first one. And what you noticed is that sigma is unknown, but we have sample data. And so you can estimate sigma by S. But S means that you should use the T version of the confidence interval, and CI tends to be my abbreviation for confidence interval. And so I haven't actually done any calculation. I just did a lot of thought work that you guys already did. But in case you weren't following, that was essentially how you should have thought. So now, let me just check that I didn't change any values. 17, 23, 20, 20, 29, 22, 19, 25, 20, 15. All right, good. So, so it's the same data as problem one, which is good because I know that X bar is 21, so we don't need to recalculate that. But we do need S. I tend to calculate S squared first. And remember, there's two versions of the formula you could use. I tend to like using this one. But this is my preference. You do happen to have integer valued data and integer valued mean. And so using the basic one is fine. So I'm going to calculate it, but I'd like you guys to see if you could get at yourselves simultaneously. Then we'll see if we get the same answer. I'm going to pause and give you guys a minute or so to try to get it. All right, so I know a few of you did get an answer, which is great. And that answer for the variance was 16, which means your standard deviation is 4. Let me give you some of the numbers that you should have gotten if you were using the formula that I've got up here. And so I got a sum of squared values to be 4,554. You want to subtract from that 10 times the square of the mean, so that's 21 squared, and divide that by 10 minus 1, or 9. This comes out to 16, which means that S is going to be the square root of that, which is 4. All right, so we've got X bar, we have S, we know N. The only thing that we don't have in this second confidence interval formula is our T star, our critical value. So the thought process to get at that is identical to what we did with problem 1, even though it's a different table. And what I mean by that is we want a 90% confidence interval here. So I tend to do a sketch of a bell-shaped distribution centered about 0. I put all of the confidence level, 0.90, in the middle. And I need to figure out what is the T star value such that the area between plus and minus that T star is 0.9. If there's 90% in the middle, there's 10% or 0.1 not in the middle. And by symmetry, that 0.1 is cut in half, and there's 0.05 on the left and 0.05 on the right. Now, even though my picture isn't perfect, it would be perfectly symmetric, and so those two areas would look the same. So hopefully your image is a little better than mine. Now, remembering that the t-table uses upper tail probabilities, it shades in way to the right, I'm going to look at the value of 0.05. What's my degrees of freedom for this problem? I see one person said 9, with hopefully more caught on to that. So it's n minus 1. N, again, is the number of data values. There's 10 values. So 10 minus 1 gives us 9. We're going to need that. And we need that by going to our table. Make sure you go to the correct one. I've got the t-table listed first in here. And so I'm going to look under the 9 degrees of freedom row, which is about there. And in the 0.05 column, because that is the upper tail probability, so that is this region here. And I look for the intersection, and I see in the 9 degrees of freedom row, I find that value in that row in that column. That is my critical value, 1.833. So that's what I'm going to take. That's my T star. It's 1.833. Now I have everything I need in order to get my upper and lower bound. So according to the formula, mu is between 21 minus and 21 plus. T star is 1.833. S is 4 divided by the square root of 10. And so I've plugged in all the details. What's left is to just calculate them. So go ahead and calculate those. Make sure you finish it. I'm gonna write your answer here, but you should make sure that you're actually able to get it. So I have a lower bound of 18.68 and upper bound of 23.32. Is anyone getting either of those values? All right, I got one response. Anyone else?
Wait, how did you get 1.833 again? Is that the chart?
Mm-hmm. Yeah, critical values, anything I label with a star, so T star, Z star, those are table lookups. They're not they're not calculations.
Is that, can you go back to the where you wrote out, where you drew the graph and stuff?
Mm-hmm. This part?
Yeah. So you look on column, wait, you look on the 9 on the,
Oh, you want the T table.
yeah, right.
I know my shading went a little bit outside the bounds. Let me beautify that. There we go. That's about the thickness I should have used. All right, no one else responded on the chat. Guys, please post, let me know that you are able to use a calculator in order to get the values that, that you should be getting. Arnold, are you all right? Tony, thank you. Anyone else? Or are you having issues? If you're having an issue, let me know that too. Yup is a positive, Sydney, right? Yup, you are good. I'm interpreting that to mean. Okay, so let's interpret our answer. Before we interpret, actually notice how it differs from the confidence interval that we got in the first one. And so when we knew the population standard deviation, our interval ranged from 19.7 to 22.3. And here it's a bigger interval, it's wider. So it goes from a lower value to a larger value. So there's more numbers contained inside. And both intervals are 90% confidence intervals. So the confidence level didn't change. The only thing that really changed was, did we know the population standard deviation or not? And that impacted which critical value table we use. And when we did know it and we used a critical value of 1.645, we got one answer. And when we didn't know the population standard deviation, we had a larger critical value. And that's because in number one, the only thing being estimated was X bar. Sigma was known. And so there's some error inherent in the process because we had to estimate the population mean with the sample mean. But now we're estimating not only the population mean, but we're also estimating the population standard deviation. So there's more error in the scenario, which results in a wider interval. And so that is conceptually what happened and why. All right, now.
Wait, why? Oh, sorry.
Why what?
You know where it says n times x to the -2 on the s squared?
You mean n times the square of the sample mean, x bar squared?
Oh, I thought that was a negative. Okay.
No, it's x bar. It's not a tick mark. All right, so let's go ahead and interpret this. Interpretation is the same pattern that I introduced the last class. And so we are, say how confident we are. We are 90% confident. That, and then the second part, interpret what the parameter in the middle means. So what is mu? Mu is the mean lifetime of brand X batteries. So we are 90% confident that the mean lifetime of brand X batteries and then finally, tell me about where that value should be. So is between 18.68 and 23.32 hours. So you notice the format is essentially the same as what we did in number 1. Some of the values changed, and that's about it. Now let's go back and take a look at number 2. So number 2 says men tend to sleep an average of 7 hours a night. Past research has found that the number of hours women sleep each night has a standard deviation of 1.5 hours. A sleep study recorded the number of hours that each of 50 females slept in a night. And found that on average, they slept 9 hours. Is this sufficient evidence to say that females sleep more than males? Support your answer with a 99% confidence interval. All right, so as I read through, you may have noticed that I started to jot some information down the side. And that's just because I tend to think it's good practice to write down what you know after reading a problem or rereading it. There's 1 or 2 numbers that I didn't write down, and that's just because I could realize, well, other than having done this problem before, I could realize it doesn't seem to fit with most of the information. And so in this case, what I'm referring to is I didn't put 7 anywhere. And that's because that 7 has to do with men, whereas everything else in this problem is about the women. And so the challenge for students is to figure out what are the appropriate labels for this information. So let's start off with what's usually the easiest. What is 50? How should that be labeled? So Miku says N, which is right. So this is your sample size, and sample size is little n. The next easiest is 9. What is 9? What label should that have? So 2 people got responses in and they're the same. Tony and Miku, you both say X bar, which is also correct. Tony, how did you deduce that that is an X bar? Why isn't that mu? So it says average, but you know 2 averages now. You know X bar and you know mu. Why isn't 9 mu? Miku, do you happen to know why? What is it that cues you in to that being X bar and not mu?
It said it was a sleep study with 50 females, so it's just a study.
So it's a study, and that 9 is the average of the sample. I think that's essentially what you're saying, which is perfect. That's how you should be thinking. And so then, if you don't recall, you go back to this wonderful table on the last lesson, and you say, okay, well, if it comes from a sample, it's a statistic, and the mean or average of a sample is X bar. That's the thought process that you guys should be going through, and you'll see why if it's not clear with my next question. So that's X bar, and that is, what is 1.5? What's the right label for 1.5? So I see 1 vote for S. Any other in agreement or differ? So far 1 and 1, 1 for S, 1 for sigma. I think there's about 11 of you on here. So anyone else with a vote? So 2 for S, 1 for sigma. Alvin, I'm not just sure if you're just supporting the guys, but it's 2 for S's, both male, 1 female for sigma. Anyone else? You are allowed to go cross-gender in this one. All right, well, the one lady has it. It is sigma. Miku, do you have a rationale for why sigma and not S?
I don't know if this is like gonna work every time, but I just look if there's like a number of people in the study, and if there's not, it's like known.
Yeah, it's a decent way of thinking about it. In general, if you're given information that either clearly comes from the population or it's given in a way where it's like past research, it has been shown, it is known, it's well documented, you know, very broad phrases like that. That's about the population. That's saying, hey, here's some big picture information. So that 1.5 came in the sentence about past research. So that is your population standard deviation. Another detail, and you might like this mental organization, is that when you learn of that 1.5, you don't even know of the sample yet. It's after that statement that you learn about the sample and some information about that sample. So you can't relate the 1.5 back to the sample data. And so here you have sigma 99.99, which is 99%. That's the confidence level that's given. That is your 1 minus alpha. And so now we have sigma, we have n, we have x bar. What table are we going to use? We need a critical value. Where is it coming from, Z or T? The difference, so Alvin asks, what's the difference? And in this table, you'll see that sigma comes from a population and S comes from a sample. So remember, population is the whole group that you are interested in, that you want to learn something about. Sample is the small part of that group that you were able to actually look at. And so in this context, for problem 2, the population would be all females. I'm sure there's more than 50 females. Those 50 females is just a small group of them. That's your sample. Alvin, does that clarify? All right, great. All right, so the question I had posed to you was, which table are you going to get your critical value from? Is it going to be Z or T? I see 1 vote for Z. Anyone else? So Z is right, and that is because sigma is known. We have sigma. So if you look back at your formula options, the only one with sigma in it is that top one, and that has a Z star in it, which means you need to use your Z table, which is the standard normal table. And so that is, whoops, sorry, I skipped the problem. That's what we're going to use here. So we need to find Z star. We need to know what is that value. I'll do the sketch on the side over here. So you've got the sketch of the normal distribution, standard normal, because we put 0 in the middle. You have 0.99, your confidence level, as the area in that center region. and we want to figure out what is the Z star value such that the area between plus and minus that value is 99%. With 99% in the middle, 0.01 is not in the middle, and half of that, or 0.005, is in each tail. So you go to the correct table, which again is your Z table. And the Z table again gives you less than probabilities. I know that the area to the left of the value I want is 0.005. I know that 0.005 is a probability, and in this table, probabilities are the main body. So I'm going to look for 0.005, and I see that it is between these two. So it's not in the table, but it's between two numbers. It happens to be perfectly in between. 0.005 is 0.0001 away from the left highlighted value and same distance from the right highlighted value. So it's right in the middle. I could see that in that row, that corresponds to a Z-score of negative 2.57 and negative 2.58. Now, since 0.005 is in between those probabilities, a good estimate for its Z-score is going to be the Z-score in between those two Z-scores. So the average of 2.57 and 2.58 is 2.575. So that's what I'm going to use for my critical value.
Could I ask a quick question?
Sure.
So in the table, it was negative, but since are we ignoring it because it's symmetric?
Yes, so you could think of it that way, but I'm also ignoring it because if you look at the formula, one is negated and one's negative, one's positive. And so if you use negative 2.575, then you're still going to get the same values. It's just you're going to get the larger value on the left and the smaller value on the right. Make sure that when you actually write your interval, you put the smaller one on the left and the bigger one on the right.
Okay.
So, so it really won't matter the sign you put to the critical value for a confidence interval.
Okay, thank you.
That's why I just make it positive at this point.
Okay, thank you.
You're welcome.
But this is 0.005 from yeah.
What's your question, or was that the question?
And then you look on the chart, right? That's
Make sure you're looking at the right chart. It should be your Z table, not T.
well, this is Z table. Oh,
Are you looking at the right table?
wait. Shoot, Z table. Wait, is this because it says like Z?
Okay, yeah, if it says Z, then it's the right table.
No, I mean like because it says Z. You look at the.
No, it's not because it says Z. I wrote Z, but I wrote Z because we know sigma. That's your thought process. Sigma is known, so use the Z table. Let me write that. That's why we're using the Z table. It's not because I wrote a Z star. All right, so we have all the information we need in order to now calculate our bounds for this confidence interval. I'm just plugging into the formula. And so you're going to calculate your small left value and the larger right value. And again, you should make sure that you are able to get the same values that I'm reporting here. But I got an interval that mu is between 8.45 and 9.55. Right, so when you're interpreting this, it's the same process. We are how confident? How confident are we?
99%.
Yes, we are 99% confident that. What does mu mean in this context? Is it average IQ? Is it mean weight? What is it? Good, Miku. Yeah, it's the mean number of hours that women sleep in a night. So that's what we want to write. We are 99% confident that women sleep on average. And now you put in your interval bounds, 8.45 to 9.55 hours a night. And so that finishes the confidence interval. Now this problem happens to come with a question, and the question is this sufficient evidence to say that females sleep more than males? What do you think? Can we say that females sleep more than males? So Sydney and Miku, you jumped to the answer yes. Can either of you explain why? So Sydney said because the average for women is higher than the average for men. Maybe. Can you answer with respect to the confidence interval? Because even though 9 is greater than 7, what about the interval? All right, perfect. So Miku points out that even the lowest value of this interval, remember, we are 99% confident that the true value for mu is some number in between 8.45 and 9.55. So almost certain. There's only a 1% chance that it isn't. So for any value in that interval, it's going to be more than 7. That's what you want to look for. So let me write that out, and I'll put that on the left side here. Since the interval is above 7, there is evidence that women on average sleep more than men. All right, so this problem happened to require a little bit more than just our general interpretation of the interval, because it came with another question that it wants us to answer. So if you have a problem like this, make sure you're answering, you know, any questions that are posed in it. So we've gone through 3 of these problems in this handout. There are a number more. Any questions having gone through 3 of them? Okay.
Actually, sorry.
Okay.
Quick question.
Yes.
So say your interval was like, for some reason, it was like 6.45, less than mu, less than 9.55. What would you write for your sufficient? So you would just say not, this is not sufficient evidence.
Right, because 7 is in that interval. So
Okay.
that means that mu could be 7.
Yeah. Okay. Yeah. Thank
7
you.
is average for men, mu is the average for women. So statistically, they could be the same. There isn't
Okay.
evidence that mu is going to be greater than 7.
Okay. Thank you.
You're welcome. Good question. All right, so take a look at 4. A student obtains 30 books from the school library and records the publication date for each. Based on the data collected, the books are on average 23.8 years old with a variance of 67.5. Create an interval estimate where alpha is 0.01. Remember that the confidence interval is 1 minus alpha, so that means it's asking for us to create a 99% confidence interval. So we want an interval estimate for the mean age of books in the school's library. So this is telling us we want an interval from mu. Just in case you weren't sure whether you wanted it from mu or p, that is one hint that this is going to be an interval from mu. So as I did with the last problem, I wrote down some information that's contained here, and I need to figure out what are the appropriate labels. Can anyone tell me any of the labels? So N is 30. That's right, Sydney. So your sample are the books, and you have 30 of them according to the first sentence. So we've got 1 down. Can someone give me another one of the missing labels? And Miku, yes, X bar. So since the average provided came on the data collected, which is your sample, that 23.8 is the sample mean, which is X bar. And notice that the variance information is in that same sentence, so it must also come from the sample. So what's the appropriate label for that variance? Remember, it's a variance, Miku, so it's a little different than S. What is it? S squared, yes. So it came from the sample, so we know it's an S something and it's variance, so don't forget to square it. So it's important to recognize what you have and where it came from so that you give it the right label. A common mistake is to call it S. So, but it's clearly so told that it's the variance. So we have N, we have X bar, we have S squared. The S squared tells us we're going to be using what, Z or T?
Is it Z because n is greater than or equal to 30?
Depends on the textbook you're going by. I tend not to teach it that way. I know that in the table, I don't remember how your book does it, but in the table that is a path, that's an estimate. It's not a bad estimate, but you'll notice that as n gets larger, t approaches z. That's why the estimate's done. But let me actually go to the table and demonstrate this. All right, so you guys saw in problem 1 for a 90% confidence interval that our z star was 1.645. And so if you look at your t table for a 90% confidence interval, there's a z star of 1.645 in the z star row. But if you go up in that column, you might feel, okay, 1.646 is close. Maybe you even feel 1.66 and 664 are close. You know, so it's a decent approximation there. You might even go so far as to feel that 1.699, 1.7 is really close to that. But at 30, you know, we're at 1.697. So if you feel that that is close enough, then fine, it's an okay approximation. I don't know how picky web work will be. I'm not sure exactly what the thought process is, but I'm sure you'll discover it very quickly. So I don't know if they approximate it with a Z or if they are more accurate with the T. I tend to do it the more accurate way. And so I really judge based on whether sigma is known or not. I don't really consider the sample size. So I know, Miku, that might be a somewhat wishy-washy response. If you go by the table that I have above, then sure, you could approximate with Z. But if you really want to be more accurate, which is the way I'm going to demonstrate it for you guys, I would say just think about whether sigma is known or not. And for problem 4, sigma is not known, and so I would use the T table. So we've got n x bar, we have s squared, which gives us s pretty quickly. And so we need t star. I'm gonna pause the video for a minute just to give you guys a chance to see if you could find your critical value. And so again, try to work through, draw a picture, a sketch like I did in some of the past problems, figure out the area that you want to use. Don't forget you're gonna need degrees of freedom, and see if you can get the right value for your critical value. Okay, so let's take a look here. And I know that we are looking in the 0.005 column because we are doing a 99% confidence interval. So there's 0.01 not inside, or half of that 0.005 on one tail, on each tail. And so there's 0.005 that I'm going to be looking for. So it's that column. And with 30 subjects, degrees of freedom is going to be 1 less, which is 29. So I'm looking in this row. which the intersection is at 2.756. So great job. All right, so now we've got every detail that we need. This is 2.756. And so I am going to pause the video again and give you guys a chance to actually put your confidence interval together and take a hand at interpreting it. So get mu between what two values and try to interpret it on your own. And we will return in a few minutes for that. 2. Okay, so the solution may have magically appeared and many students were able to get at it, which is great. Your confidence interval should be that mu is between 19.67 and 27.93 if you plug into the appropriate formula that uses S. So a common mistake is forgetting to square root the 67.5 value. So some of you may have fallen into that trap. But once you get this interval, interpreting it, we are 99% confident that the mean age of books in this library, your population aren't all books in the world or the US, it's this particular library. So the mean age is between 19.67 and 27.93 years old. And that is number 4. Which what?
Is this like similar to question 3?
Only in the sense of using the t-table.
Oh, but you also have to find s squared, right?
Well, I mean, you could have just jumped straight to the square root. My preference is to get the variance first and then square root that. But a lot of times students will just write S equals square root of that formula that I have there. So, you know, many students may just jump to it directly, which is fine. It's just my personal preference to get the variance first and then square root that.
Wait, how did you use the variance and how'd you use the variance to solve for it again?
How'd I get the interval?
Yeah.
With the second confidence interval formula there. So notice that it uses S, but variance is S squared. So how do you get S from S squared?
Oh, you squared?
Square root.
Oh no, square root it.
Yeah. All right, so you've got 2 more. And let's take a look at number 5. So I like 5 because it's really short and to the point, but it has a lot of information in it. And you'll see what I mean as I go through. Number 5 says that a coin is tossed 10,000 times. And the number of heads is recorded. It is found that the number of heads is 5,167. And we want to know, is this a fair coin? Prove with a confidence interval. If it is fair, what would you look for? What does it mean to be a fair coin? Not a trick question. What does it mean for a coin to be fair? Heads comes up half the time. Good. So that comes up value is 0.5. That 0.5 is a probability proportion. You could think of it either way. And so this means if fair, then P can be 0.5. So that means we want a confidence interval for P. Right? So that's the thought process. You always have to figure out, are you doing an interval for mu or P? And this is the first time that we actually want an interval for P. So let's take a look at the confidence interval for formula, which is the third one. So the confidence interval formula uses P hat, Q hat, N, and Z. P hat, Q hat, N, and Z. Now P hat is our sample proportion. Or in other words, for this problem, what is the proportion of the 10,000 tosses that came up heads? Good, so Miku wrote 5,167 over 10,000. Formally, P hat is a count over a sample size. And so that's essentially what Miku just did. And so we have 0.5167 for the sample proportion. Q hat, you could think of as the complement. So P hat is the proportion of heads, Q hat is the proportion of tails, which is 1 minus P hat, or 0.4833 for this problem. So we have N, we have P hat, we have Q hat, Z star was the only thing remaining. And alpha, or the confidence level, wasn't given. When it's not given, the default is for 1 minus alpha to be 95%, or 0.95. And so that's always going to hold, whether this is an interval for P or mu. Right? So if the confidence level isn't given, default to 95%. So now we need Z star. And you find it the same way that you did or would have for an interval for mu. So I'm going to pause the video again, and I want you guys to find the critical value for this problem. And if you feel confident in it, feel free to apply the confidence interval formula in order to get your interval for P. And we will return in just a moment. Okay, so I know that, that there is some issue with this problem, or at least getting the critical value. The correct value at the 95% confidence level is 1.96. The picture that you should have sketched should look something like this. And you're looking for your Z star value such that the area between plus and minus it is 0.95, which means 5% is outside, or 2.5%, 0.025, is in each tail. Again, a quick check is to add up all three of those values, and it has to equal 1. Otherwise, a mistake was done somewhere. And so the standard normal table gives us less than probability, so I'm going to look up 0.025 in the standard normal table. So I'm looking for 0.025, which is exactly in the table right there. And that row has negative 1.9 for the first, up to the first decimal place of the Z-score, and 6 for the second decimal place. So 1.96 is the right answer. And that's how you get at it.
Wait, can you repeat that?
You're looking for 0.05, which is a probability, and probabilities are in the body of the table. So you're looking for, sorry, 0.025. So you're looking for 0.025, which for this case is exactly in the table. It's right here. And you're finding the corresponding Z-score. So you're working backwards. Instead of using a z-score to get a probability, you have a probability that you're going to get its z-score. And you'll see that's in the negative 1.9 row and 0.06 column. So negative 1.96 is the z-score. For confidence intervals, since you're adding and subtracting, just using the positive version is fine. So that's why I wrote 1.96 here, which you would then plug in to your interval.
Wait, is it because like it's symmetric, or like how it's, you know what I mean? Like it's 0.025 on both sides. So that's why, is that why you could write 1.96? Like,
And that's why I could look up 0.025 in order to find 1.96. I'm not sure if that's your question. If you could think of another way of asking your question, I'm happy to try to tackle it.
but what do you do about the negative z?
Oh, it doesn't matter about the negative sign because you're going to add and subtract anyway. So when you plug into the formula, one of those values will be large and one will be smaller. So just make sure that when you actually write your interval, have smaller value on the left and bigger value on the right. So here I took that formula on the first page and I plugged in all of the appropriate values. And of course, as usual, what's left is to calculate. And when you calculate, you should get the interval for P to be between 0.5069 and 0.5265.
How do we know what to round it to?
This case, it's important to be more exact because if you round to the first decimal point, you're going to get the wrong answer. And
Okay.
Typically when I'm dealing with proportions which are related to probabilities, I tend to do 4 decimal places because that's often that's what you have in the Z table. You have at least 2 decimal places in the T table. So it's, I think 4 decimal places for proportions and probabilities is a good length.
Okay, thank
Good
you.
level of accuracy. You're welcome. And then interpreting is the same process. There is, an inherent question in this problem too, but let's just do the general interpretation. So we are 95% confident that the probability of heads for this coin is between 0.5069 and 0.5265. Now remember that what we're really interested in is knowing, is the coin fair? Anyone have a thought? So Miku quickly said no. Miku, you want to finish the thought off? Why no?
Because 0.50 isn't in the confidence interval.
Perfect. So remember one of the first questions I asked right here. Whoop, sorry. Just above that. Right here was, what does it mean for the coin to be fair? And in general, you guys said, oh, it means that P could be 0.5, that the probability of heads would be 50% or 0.5. And so here we have an interval for the probability of heads for this coin. But according to this interval, P cannot be 0.5 because 0.5 is not inside the interval. And so that's exactly what we want to say. We note, since 0.5 is not in the interval, the coin is biased. Or you could just say not fair, both they mean the same thing. Now the question doesn't ask this, but I will. What does the coin favor? Does it favor heads or tails? Good, Miku. Yeah, it favors heads. Remember, this interval for P was developed from P hat. And P hat was our sample proportion of heads, which means P is the population proportion, which is an awkward way of saying probability of heads for this coin. And that probability, no matter what value it is in that interval, is larger than 50%, which means the coin favors heads. So I'm just going to put that note in here. The coin favors heads. There's one last problem, which we've got time to finish here. And that is that on a recent exam, students were asked to predict their letter grade for the test. Of the 46 students that made predictions, 20 of them overestimated their grade. So, they, for example, said, oh, I think I got a 90, but they really got an 82. They thought they did better than they did. Create an interval estimate where alpha is 0.1 for the percentage of students that are overconfident in their performance on exams. All right, so is this going to be an interval for P or mu?
Wait, interval for what?
For proportion or mean? That's my question. I see one response for P, which is right. Miku, is there something in this that indicates that?
I know that 20 of them overestimated their grade, so that's 20 over 46 is P hat.
Good, so you could get a proportion, but it's also asking for an interval estimate for the percentage of students. So percentage is another signal that you want interval for P. And this, by the way, is a real study that I did. So I was actually curious enough to investigate this. I believe the numbers are what I actually found. So Miku kind of gave some extra information. She noticed that there are 46 students, so that's your sample size. You could get the proportion of that sample that were overconfident, which was 20 over 46, which means that Q hat is 26 over 46. It's 1 minus P hat. And alpha is given as 0.1, so 1 minus alpha, your confidence level is 1 minus 0.1 or 0.9, 90%. And from problem 1, which also used 90% and the z-table, just in case you don't have that one in your notes, what was the value of the critical value that we used for the 90% confidence interval from z? Good, Alvin. Yeah, it's remember, it is this detail in the formula, or it is labeled in the bottom right of this slide that I've got up. So 1.645. So we have the same critical value. So that's 1.645. So at this point, I'm going to pause the video again. You've got all the information you need in order to get your intervals. So that's what I want you to do, is I want you to figure out what are the two values that P is between and give the interpretation a shot. And I will return in a few minutes.